Hello, everyone. So in this Chapter 9 lecture, I'm going to be introducing you to an entirely new bonding model, an alternate to the last one, which was the localized electron model. This new model of bonding, which is very different, is called molecular orbital theory. So before I get into molecular orbital theory, I wanted to just remind you of what that last model was. It was called the localized electron model, and it also involved the hybridization of orbitals. And we found out that the essential functioning of this model was that bonds are formed simply by the overlap of atomic orbitals. Atomic orbitals overlap. They could be the original atomic orbitals. They could be hybridized atomic orbitals, but we had overlap of the atomic orbitals ending up with a pair of electrons in the overlap region, and that produced the covalent bond. Now, we are looking at a different model, which I'm abbreviating here as the MO model, molecular orbital model. As it turns out, in this model, there are no atomic orbitals at all. Atomic orbitals are possessed by atoms, but we're dealing with molecules. And what we find in this model is that molecules don't have atomic orbitals, molecules have molecular orbitals. And these molecular orbitals encompass the entire molecule. So we're not dealing with atomic orbitals at all. All right, atomic orbitals are for atoms, molecular orbitals are for molecules. So now the question is, well, how do we know what the molecular orbitals are for a particular molecule? Well, we have to figure it out. And the way we figure it out is ultimately by taking combinations of the atomic orbitals of the atoms in the molecule. So it turns out that these molecular orbitals in our molecules ultimately can be described as resulting from what we call the linear combinations of all the atomic orbitals of all the atoms in the molecule. I'm going to highlight that. Let's pick an unusual color. Let's go purple. So molecular orbitals result from the linear combinations of all the atomic orbitals of all the atoms in that molecule. And I'm going to get a color here. Let's go with purple. Linear combinations of all the atomic orbitals is often abbreviated LCAO. It's the technique we're using. Linear combinations of the atomic orbitals, LCAO. So what does this technique involve? Well, it involves taking the wave functions of the original atomic orbitals and either adding or subtracting them to obtain new molecular orbitals. And that's what it says right here. This is achieved by adding or subtracting the wave functions that describe the atomic orbitals. So let's remember that an atomic orbital can be mathematically described by an equation known as its wave function. And it turns out that we can either take those wave functions of atomic orbitals and add them, or we can take those wave functions and subtract them. Now, I'm going to give you a very basic visual to understand what I mean by adding or subtracting wave functions. It turns out that adding wave functions together, corresponds to what we would call constructive combinations of atomic orbitals. Constructive combination or constructive interference. So I'm going to write constructive combinations of atomic orbitals, and it produces what are called bonding molecular orbitals. Bonding molecular orbitals. Now, I'm going to illustrate this principle by using very simple waves. So let's think of a regular wave, a water wave, for example. We can visualize waves of water better than we can visualize the wave functions of an atom. I'm not sure if you guys remember this, but the symbol for a wave function is the Greek letter psi. Now, let's suppose we have a wave, this wave over here, and let's suppose this wave represents the atomic orbital of one atom. And the wave function, let's call it atom A. Let's try that again. Let's call this psi A, the wave function of our first orbital. And we have another orbital, which I'm going to represent with this wave over here. And let's call this wave function psi b for our second orbital. Now, if you notice, the way I've aligned these two waves here are such that the peak of wave A lines up with the peak of wave B, and the trough of wave A aligns with the trough of wave B. That means that these two waves are in phase with one another. And if you take these two waves and they're in phase and you combine them together, well, what happens? Well, you get constructive interference. And constructive interference produces just one bigger wave. And I'm going to represent this constructive interference using a plus because we are adding our wave functions together. And we get this constructive interference and we get this new wave here. Well, let's think of this new bigger wave as a bonding molecular orbital. So we get a bonding molecular orbital. I'm going to use MO for molecular orbital. Now, it turns out that bonding molecular orbitals will always have lower potential energy and be more stable than the original atomic orbitals that were combined together. So let's note here has lower potential energy and is more stable than the original atomic orbitals. I'm going to use AO as my abbreviation for atomic orbitals, original atomic orbitals combined. So this was adding wave functions together, constructive combination, and we get bonding molecular orbitals. But just as I added these, I could have done the opposite. I could have subtracted the wave functions. Now, if I subtract the wave functions, this ends up being equivalent to the destructive combination of my atomic orbitals. And when we destructively combine atomic orbitals, the result is known as antibonding molecular orbitals. So over here we produce antibonding molecular orbitals in contrast to bonding molecular orbitals. So once again, using these two waves as representations of my atomic orbitals, the wave function of one atomic orbital, the wave function of another atomic orbital, but this time, even though they're the exact two waves that I showed in the previous example, notice now that the crest of wave A is now aligned with the trough of wave B. The trough of wave A is aligned with the crest of wave B. And so these two waves aren't in phase, they are out of phase. Now, if we combine these two out of phase waves, well, what do we end up with? Well, what's going to happen to these waves? They're going to cancel each other out. And so what we have here is an example of destructive interference. And the result is known as, at least if we're working with atomic orbitals, the result of this destructive interference is a antibonding molecular orbital. So that's what we have over here. Antibonding molecular orbital. An antibonding molecular orbital is typically indicated with an asterisk. So anytime you see an asterisk beside a molecular orbital, it's an antibonding molecular orbital. And, well, maybe not surprisingly, antibonding molecular orbitals have higher potential energy and are less stable than the original atomic orbitals combined. So this has higher potential energy and is less stable than the original atomic orbitals combined. So just by using simple wave drawings, very simple two-dimensional waves, we can see the difference between combining those waves together in phase, constructive interference, versus combining them out of phase, which is destructive interference. And in one case we produce, if we're talking about orbitals, which are not quite analogous to two-dimensional waves, but I'm just trying to give you an analogy here. If we're talking about orbitals, atomic orbitals can combine constructively in phase, producing bonding molecular orbitals, and atomic orbitals can combine destructively out of phase, and we end up with antibonding molecular orbitals. Now, molecular orbital theory is a pretty difficult theory to wrap your head around. And so to make our lives a whole lot easier, we're only going to be applying this model to homonuclear diatomic molecules. So a homonuclear diatomic molecule is a diatomic molecule composed of the same two elements. For example, diatomic nitrogen, N2, or O2, or H2, or Cl2, etc. And we're going to be applying it such that the valence atomic orbitals of each atom, and there are only two atoms combining together, the valence orbitals combine to form the molecule's molecular orbitals. Now, when we combine valence atomic orbitals together, all right, to form molecular orbitals, there's certain conditions that must be met. The first condition that must be met is that the combining atomic orbitals should have nearly the same energy, either identical energies or almost identical energies. So, for example, if I was to take a 2p orbital and try and combine it together with another 2p orbital, these are 2p orbitals on two different atoms combining together. Well, this would be allowed because these two orbitals have essentially the same energy. However, if I was to take a 1s orbital and try to combine it with a 2p orbital, well, that would not work in molecular orbital theory. So that is a no-go. And that's because there is an appreciable difference in energy, all right, between the 1s orbital and the 2p orbital. So let's note that over here. All right, this is because there is an appreciable difference in energy. The second condition that must be met when we combine atomic orbitals together to form molecular orbitals is that the combining atomic orbitals should have the same symmetry around the molecular axis. So what is meant by this? Well, for example, if we were looking in a 2p subshell, well, there are three orbitals in a 2p subshell, the px, the py, the pz. And if I took the 2px orbital on one atom, if I was to do a successful combination, it would have to combine with the 2px orbital on the other atom because they're both along the x-axis and therefore they have the same symmetry around the molecular axis. So px, px, same symmetry. But if we try to combine, say, a 2px orbital with a 2py orbital, well, that just would not work for the theory. That's not going to happen. And that's because, in this case, well, we've got x-axis, the y-axis. These orbitals do not have the same axis of symmetry. So, different axes over here. Okay, well, now let's start looking at what sorts of bonding and anti-bonding molecular orbitals we get from the combination of the valence orbitals of two atoms, because we're only dealing with two atoms, because we're only working on diatomic molecules for this particular section of the course. So let's just scroll up to the next page here. So the first thing we're going to look at is the formation of molecular orbitals from the combination of s valence orbitals. S valence orbitals. Let's highlight S. I'm going to highlight it in something fun. Orange. S valence orbitals. So what we have here are two s orbitals. Let's get a pen that we can write here. Here we go. So this is an s orbital and this is an s orbital. These are both atomic orbitals. Now let's suppose two atoms are going to bond. Well, their s orbitals are going to combine together. Now let's note in this particular example that the s orbital and the other s orbital are approaching each other in a classic head-to-head configuration. So we've got the old head-to-head scenario. Now, when these orbitals combine together, as we've seen, we're thinking about the wave functions of these orbitals. Now, the wave functions can be added or subtracted, which means that these two orbitals can be combined constructively and destructively. So what do we end up with? Well, what we end up with are two new molecular orbitals. And these are the two new molecular orbitals that we end up with. Okay. One of them is ended up by undergoing constructive interference. I'll use a plus for constructive combination, and the other orbital is obtained by the destructive combination of the atomic orbitals, constructive and destructive. And what we end up with are two new molecular orbitals. So what are these two new molecular orbitals? Now you're saying two. I don't see two. Well, this is one molecular orbital. And even though this looks like it's more than one, this whole thing is one molecular orbital. So 1, 2 molecular orbitals. And the little black dots here, they represent the nucleus, So what do we end up with? Well, here we end up with, in the downward direction, from the positive constructive interference, we end up with a bonding molecular orbital. Now this bonding molecular orbital is known as a sigma molecular orbital. Why? Because it was produced by head-to-head combination. So this is a sigma, and we call it a sigma S bonding molecular orbital. Meanwhile, the orbital that we obtain from the destructive combination of those two s orbitals, well, this is an antibonding molecular orbital. And it is a sigma star. Let's remember we use this asterisk if it's an antibonding orbital. So it's a sigma S star antibonding molecular orbital. Note that the bonding molecular orbital has lower potential energy than the two original combining atoms. So if we think of this axis here as an axis of potential energy, the bonding molecular orbital has lower potential energy. The antibonding molecular orbital has higher potential energy. Let's also note that there is a very high electron density between the nuclei in the bonding molecular orbital. And that high electron density that we see between the nuclei promotes bond formation. It promotes bonding. So I'm going to write that down here as well, that we have a high electron density between the nuclei promotes bonding. In contrast, when we look at the antibonding molecular orbital and we look at the space between the nuclei of our atoms, well, it's pretty bare, that space. So we don't have any electron density, well, barely any electron density between these two nuclei, all right, which means there isn't going to be support of bonding by that antibonding molecular orbital, and that's why it's called antibonding. It does not promote bonding because of that lack of electron density in between the two nuclei. Okay, so that's the formation of molecular orbitals from the constructive and destructive interference of the s valence atomic orbitals of two bonding atoms. But some atoms have s and p valence orbitals. So suppose now we are going to combine p orbitals together. Okay, so let's take a look at what happens when we combine p orbitals together. Well, let's remember that an atom will always have three valence p orbitals, the px, the py, and the pz. So if the px, the py, the pz on one atom are going to now combine constructively and destructively with the px, the py, and the pz orbitals of the other atom, well, what do we end up with? Well, what we are showing here in this diagram is the py orbital is the blue orbital along the y-axis. Let's show that a little more clearly. The px orbital is this sort of yellowy green one. Whoops, I should say x, which is along the x-axis. And this one that's sort of going diagonally, that's coming out of the page, going into the page, well, that clearly is our old friend, the pz orbital. So let's color code it, pz, pz. Okay, now let's start pushing these orbitals closer and closer together. Well, if we do so, how are they going to interact? Well, clearly, if the px gets closer and closer together with the px orbital on the other atom, these orbitals would be interacting with one another in a head-to-head configuration. So over here, we've got head to head. But that is not the case for the py orbitals, those blue py orbitals. As they get closer and closer and closer together, well, they're not going to be interacting with one another in a head-to-head configuration. They're getting closer and closer, all right, in a side-to-side orientation. So side to side. And how about the pz orbitals? This pz orbital and this pz orbital, are they coming at each other head to head or side to side? Well, hopefully you can see that they are also in a side to side orientation. So now let's tease it out. Let's take a look and see how the px's interact versus the py's versus the pz's in the formation of our molecular orbitals. So I'm just going to scroll down a smidge here. So in our first diagram, what I have here, let's just change colors, is a px atomic orbital that is going to be both constructively and destructively combined with another px atomic orbital. And well, let's note that these two orbitals, I don't have quite enough space in between them, are approaching each other head to head. And well, what happens? Well, they approach each other head to head, and they're going to either combine constructively or destructively. And as a result, we end up with two new molecular orbitals. One here and one here. So from the constructive interference, positive, we get a more stable, lower energy bonding molecular orbital. And from the destructive combination, we get a higher energy antibonding molecular orbital. So once again, this axis here, let's try and draw that a little more neatly, is an axis of potential energy. So we make two new orbitals. This is one molecular orbital, and this, even though it doesn't look like one, is just one molecular orbital. So let's note that these molecular orbitals were both produced head to head. And that means both of these new molecular orbitals are sigma orbitals. The lower energy orbital is the bonding molecular orbital. This is a sigma p bonding molecular orbital. And up here we have an antibonding molecular orbital, which we're going to represent as sigma p star as our antibonding molecular orbital. So we get a more stable bonding, a less stable antibonding. Let's note also that the electron density in the bonding molecular orbital is very high in between the two atomic nuclei, whereas there is virtually no electron density in between the bonding nuclei in the antibonding molecular orbital. This is why the bonding molecular orbital promotes bonding, while the antibonding molecular orbital does not promote bonding. Okay, now what about the combination of, say, the py orbitals, the py orbitals? So let's suppose I have a py atomic orbital here and another py atomic orbital here, both along the y-axis. Now, these orbitals are not approaching each other head to head. They are clearly approaching each other in a side-to-side manner. So, side to side approach. Well, once again, we're going to end up with two new orbitals from constructive and destructive combinations. And here are the two new molecular orbitals that we end up with. So constructive, low energy molecular orbital, destructive produces the higher energy antibonding molecular orbital. And again, let's just put our energy axis off to the side. Okay, here we go. Now, as it turns out, the bonding molecular orbital that we end up with is not a sigma bonding orbital. What we end up with here is a pi bonding molecular orbital. This is called the pi-p bonding molecular orbital. So if it's head to head, we get sigma bonding and antibonding molecular orbitals. But if it's a side to side combo, we get pi bonding and pi antibonding molecular orbitals. Okay. Note once again that the antibonding pi molecular orbital has essentially no electron density in between the nuclei, which is why it does not promote bonding. But over here, we definitely do have an electron density, all right, noted between the nuclei, and it does promote bonding. Okay. So we've taken a look at the head-to-head combinations of the px orbitals, the side-to-side combination of py orbitals. What do you think is going to happen for the pz's? Do you think the pz orbitals, when they combine, are going to give the same thing as the px's or the py's? Well, it turns out combining the pz's will also be side to side, and you will get, once again, a pi bonding molecular orbital and a pi antibonding molecular orbital. So I'm not going to draw that a third time. I'm just going to note that. Let's actually use the same color that I had for those PZs. So I'm going to say note PZ and PZ orbitals combine side to side, also producing pi p bonding and pi star pi star p antibonding molecular orbitals. Okay, so essentially you get the same picture for the PZs as we got for the PYs. So now that we've seen the molecular orbitals and what they look like, well, we're sort of going to forget about what they look like now. When we wrote electron configurations and orbital diagrams back in chapter 7 for atoms, we didn't show the shapes of each of the orbitals when we wrote out those electron configurations or orbital diagrams. We just used little lines or boxes to represent the orbitals. Well, we're going to do the same thing for molecular orbitals. And at this point, we're going to be producing what are called molecular orbital diagrams for homonuclear diatomic molecules. So we're going to be generating molecular orbital diagrams at this point. And we're going to focus on diatomic molecules formed primarily by elements in periods 1 and periods 2. So let's start at the top with the molecular orbital diagram. I call this MO diagram 1 that would be formed, that we would produce if we were making diatomic molecules from elements in period 1. So we're going to start with period 1 diatomics. Now, there are only two elements in period 1, hydrogen and helium. So we're talking about diatomic hydrogen or diatomic helium. Now, hydrogen and helium in period 1 only have s valence orbitals. They have s valence orbitals, that's it. Period 1, n equals 1, all we have are s atomic orbitals. So if we only have s atomic orbitals, here let's start with our atomic orbitals over here and over here. And well, the two combining atoms would be combining together their 1s orbitals. Those are the original atomic orbitals on the two atoms that are bonding together. Now, these atomic orbitals will combine, well, they're s orbitals. They're going to combine head to head. And so the resulting molecular orbitals are going to be a low energy sigma 1s molecular orbital and a high energy sigma star 1s antibonding molecular orbital. So these are the two molecular orbitals we would end up with in either the diatomic hydrogen molecule or the diatomic helium molecule. These here are the molecular orbitals for the molecule. Now, this is what you get when we're talking about our period 1 diatomics. Well, what about the diatomic molecules you could form in period 2? I thought I would underline this better, but I'm clearly not. Oh well. Let's take a look now at what we get for the period 2 diatomic molecules. oops, that should say period 2 diatomics. How about that? I was able to underline it perfectly. Ha! How about that? Now, turns out for period 2 diatomics, there are two possible molecular orbital diagrams that we could end up with. And I've called them molecular orbital diagram Roman numeral 2 and molecular orbital diagram Roman numeral 3. Let's take a look at these diagrams and see how they're obtained. And I'm just going to separate the two. Let's separate them with a little gray line to separate them. And I'm actually going to start with the diagram on the right, MO diagram number 3. So we have two atoms that are bonding together to make a molecule. And the atomic orbitals on one atom are combining with the atomic orbitals on the other atom to create molecular orbitals. So what are the atomic orbitals that we're working with? Well, in period 2, the atomic orbitals possessed by the atoms are the 2s orbitals and the 2p orbitals, 2s and 2p. So what happens when these orbitals combine? Well, the 2s will combine with the 2s because they have the same energy and the same symmetry. And will they combine head to head or side to side? They combine head to head. And when they combine head to head, we end up making a sigma 2s molecular orbital and a sigma star 2s antibonding molecular orbital. Low energy stable bonding, high energy less stable antibonding molecular orbital. Okay. Now, what happens when the two p orbitals on each atom combine together? Well, let's remember that the p orbitals are oriented x, y, and z. Now, we saw on the previous page that the px orbitals combine head to head. And when they combine head to head, we create sigma 2p orbitals. And so we're going to get a sigma 2p orbital, which is very stable, and a sigma star 2p orbital, which is very high in energy. In fact, the split is equal. The more stable the bonding orbital, the less stable the corresponding antibonding orbital is. And so these molecular orbitals are created by the combination of the px orbitals. And I'm color coding to help you out here. Now, when the py orbitals combine together, they didn't combine together head to head, they combined together side to side. And that produced pi molecular orbitals. We got a pi 2p orbital, and we're also going to get an antibonding pi 2p orbital. And these pi orbitals come from the combination of the y's in a side-to-side bonding, which is low energy, and the antibonding, low energy bonding, higher energy antibonding. Now, what about the pz's? Well, I mentioned that the pz's combine in exactly the same way as the py's, also side to side, and so we're going to produce another pi 2p and another pi star 2p molecular orbital, bonding and antibonding. And so this is the set of molecular orbitals we end up with from the combination of the 2s orbitals on the two atoms and the 2p orbitals on both atoms. Okay, now as it turns out, this molecular orbital diagram only works for diatomic molecules formed by elements in groups 6a, 7a, and 8a. So I'm going to make a note of that. This is, oops, I meant to make that a black pen. Let's try that again. So this over here is for diatomics formed by elements in groups 6A, 7A, and 8A. Well, it turns out for diatomics in period 2, in groups 1A, 2A, 3A, 4A, 5A, well, we get a similar molecular orbital diagram, but with a slight difference. And that's going to be this molecular orbital diagram number 2 over here that we're going to look at now. This diagram is going to be for diatomics formed by elements in groups 1A, 2A, 3A, 4A, and 5A. So once again, we have the atomic orbitals of the two combining atoms shown off to the side, and the molecular orbitals are shown in the middle of the diagram. And once again, the atomic orbitals combined are 2s and 2p. Once again, the 2s atomic orbitals combine to give a sigma 2s and a sigma star 2s orbital, a bonding sigma and an anti-bonding sigma molecular orbital. And well, once again, we're going to be looking at the two p's combining as the x's, the y's, and the z's. Oops, let's get the color for the z. Z. Now, once again, the px combines with the other px. And when they combine together, we get sigma bonding and sigma antibonding orbitals. But this time, the sigma 2p bonding molecular orbital is here. The sigma star 2p antibonding orbital is still in the place it was before. I'm going to draw that a little bit more neatly. Sigma star 2p. Meanwhile, when the y's combine together, we again see pi molecular and pi bonding and pi antibonding molecular orbitals produced because they're combining side to side. But now the pi 2p molecular orbital is here. The pi antibonding 2p orbital is still in the same place, however. And we're going to see a similar issue with the z's combining together. When the z's combine together, also side to side, the resulting pi molecular orbital is here, and the pi antibonding molecular orbital is here. So the real difference between these two molecular orbital diagrams is in molecular orbital diagram 2, the pi molecular orbitals are lower than the sigma molecular orbital, but in molecular orbital diagram number 3, it's reversed. The sigma molecular orbital is lower in potential energy than the two pi molecular orbitals. So you have to just remember that they're almost identical except for the switch in the ordering of these key molecular orbitals. Okay, so that's a lot to take in right now. So I'm going to stop with this lecture, and as it turns out, in our next lecture, I'm going to be showing you how to apply molecular orbital theory to very specific diatomic molecules. For example, fluorine, F2, or hydrogen, H2, and we're going to see how, to put all of this together for specific molecules. Okay, till then, take care, and I'll be talking to you very soon. Bye now.